Welcome to the lecture of research methodology. In this lecture, I'm going to discuss with you about statistical tests. My name is Wilson Yong. I'm a senior lecturer at the Biotechnology Research Institute, University Malaysia Sabah. Statistical tests are used in hypothesis testing. A hypothesis is an assumption about a value of a population parameter. This assumption may be or may not be true. Hypothesis testing refers to the procedures used by researchers or statisticians to accept or reject statistical hypotheses. The best way to determine whether a hypothesis is true or false is to examine the entire population. This is impractical in most situations, so a random sample is normally taken from the population and tested. If the sample data is not consistent with the hypothesis is rejected. The important functions of a hypothesis are to test the truth or accuracy of a theory, enhance the objectivity and purpose of research work, and help researchers in prioritizing data collection, hence providing focus on the study. There are basically two types of hypotheses. The null hypothesis states that a population parameter such as mean or standard deviation is equal to a hypothesized value. In other words, there is no statistical significance between the variables investigated. The null hypothesis is often an initial claim that is based on previous analysis or specialized knowledge. It is usually the hypothesis a researcher will try to disprove. Alternative hypothesis is simply the opposite of the null hypothesis. The alternative hypothesis states that a population parameter is smaller than, greater than, or different from the hypothesized value in the null hypothesis. The alternative hypothesis is what the researcher might believe to be true or hope to prove true. In testing a hypothesis, we compare the test statistics to a critical value called the p-value to decide whether or not to reject the null hypothesis. A test statistic is a number that describes how much the relationship between variables in your test differs from the null hypothesis of no relationship. The p-value or calculated probability estimates how likely it is that you would see the difference described by the test statistic if the null hypothesis of no relationship were true. If the value of the test statistic is more extreme than the statistic calculated from the null hypothesis, then you can infer a statistically significant relationship between the predictor and outcome variables. If the value of the test statistic is less extreme than the one calculated from the null hypothesis, then you can infer no statistically significant relationship between the predictor and outcome variables. In other words, the p-value is the smallest level of significance for which the observed data is measured. If the p-value is smaller than the significance level, null hypothesis is rejected. If it is larger than the significance level, null hypothesis is not rejected. The significance level is also known as the risk level. It is the highest probability value for which the null hypothesis is rejected. Commonly used significance levels are 0.01, 0.05, and 0.1. If the 0.1 level is used, then the null hypothesis is rejected if the probability value is less than or equal to 0.1. significance levels are normally fixed at or below 5%. A significance value of 0.05 means that the level of confidence is 95%. In other words, there is a 5% risk of concluding that a different exists when there is none, making an erroneous conclusion. Accepting a hypothesis does not mean that the hypothesis is true. It only means that the information collected does not support the rejection of the hypothesis. Two types of errors are possible in hypothesis testing. They are type 1 and type 2 errors. A type 1 error occurs during hypothesis testing when a null hypothesis is rejected, even though it is accurate and should not be rejected. A type 1 error is false positive, leading to an incorrect rejection of the null hypothesis. A type 2 error is defined as the probability of incorrectly retaining the null hypothesis, when in fact it is not applicable to the entire population. A type 2 error is essentially a false negative, or known as an error of omission. A type 2 error can be reduced by making more stringent criteria for rejecting a null hypothesis, although this increases the chances of a false positive. Analysts need to weigh the likelihood and impact of type 2 errors with type 1 errors. To determine which statistical test to use, you need to know whether your data meets certain assumptions and the types of variables that you are dealing with. Statistical tests make some common assumptions about the data they are testing. Independence of observations, or no autocorrelation, means each participant is only counted as one observation. The statistical assumption of independence of observations stipulates that all participants in a sample are only counted once. If a participant was to appear multiple times in a sample, each time as an independent observation, then the statistics would be artificially skewed in their favor and not be representative of a true sample of independent participants. Independence of observations makes sure that each participant's variance affects the overall analysis just once. The assumption of homogeneity of variance is important when conducting between-subject statistics. The assumption is that the variances and thus distributions of independent groups of a continuous variable are similar, equal, or equivalent. If one group has much more variation than others, it will limit the effectiveness of the test. The statistical assumption of normality is central to conducting inferential statistics using continuous variables and outcomes. A normal distribution resembles the bell curve, where the mean, median, and mode of a distribution are all the same. In a normal distribution, 68% of all observations will fall within one standard deviation above and below the mean. 95% will occur within two standard deviations above and below the mean, and 99.5% of all observations will exist within three standard deviations above and below the mean. The assumption of normality is tested for when employing parametric statistics with quantitative data or continuous variables and outcomes. If your data do not meet the assumptions of normality or homogeneity of variance, you may be able to perform a non-parametric statistical test which allows you to make comparisons without any assumptions about the data distribution. Parametric statistics are used when the outcome is continuous and the statistical assumptions of normality and homogeneity of variance are met. Parametric statistics provide more precise and accurate inferences. There is also more statistical power associated with the use of parametric statistics. This increase in power comes directly from the precision and accuracy found in continuous level measurement. Non-parametric statistics are used with categorical and ordinal outcomes. Non-parametric statistics are also used when the statistical assumptions of parametric statistics are violated. Non-parametric statistics should also be used when the sample size is small and the distribution of the outcome is not known and cannot be assumed to be approximately normally distributed. Parametric tests usually have stricter requirements than non-parametric tests and are able to make stronger inferences from the data. They can only be conducted with data that adheres to the common assumptions of statistical tests. The most common types of parametric tests include regression test, comparison test, and correlation test. Regression tests are used to test cause and effect relationships. They look for the effect of one or more continuous variables on another variable by fitting a line to the observed data. Linear regression models use a straight line, while logistic and nonlinear regression models use a curved line. Regression allows you to estimate how a dependent variable changes as the independent variable change. Simple linear regression is used to estimate the relationship between two quantitative variables. You can use simple linear regression when you want to know how strong the relationship is between two variables. For example, the relationship between rainfall and soil erosion, or the value of the independent variable at a certain value of the independent variable, such as the level of soil erosion at a certain amount of rainfall. Multiple linear regression is used to estimate the relationship between two or more independent variables and one dependent variable. You can use multiple linear regression when you want to know how strong the relationship is between two or more independent variables and one dependent variable. For example, how rainfall, temperature, and amount of fertilizer added affect crop growth, or the value of the dependent variable at a certain value of the independent variables, such as the expected yield of a crop at certain levels of rainfall, temperature, and fertilizer addition. Logistic regression is used to predict a categorical or binary dependent variable such as yes or no, pass or fail, alive or dead, and etc. based on a set of independent variables, although many more complex extensions exist. You can use logistic regression when you want to know the probability of a certain class or event existing. For example, the survival of a test subject after treatment with an experimental drug. Comparison tests look for differences among group means. They can be used to test the effect of a categorical variable on the mean value of some other characteristic. T-tests are used when comparing the means of precisely two groups. For example, the average height of men and women. A one-sample t-test is used to compare a single population to a standard value, for example, to determine whether the average lifespan of a specific town is different from the country average. A paired t-test is used to compare a single population before and after some experimental intervention or at two different points in time. For example, measuring student performance on an exam before and after being exposed to a test preparation program. If the group come from two different populations, such as two different species or people from two separate cities, perform a two-sample t-test, also known as independent t-test or unpaired samples t-test. It helps you to compare the means of two sets of data. For example, you could run a t-test to see if the average exam scores of two different schools are different. ANOVA, which stands for Analysis of Variance, is a statistical test used to analyze the difference between the means of more than two groups, such as the average heights of children, teenagers, and adults. A one-way ANOVA uses one independent variable, while a two-way ANOVA uses two independent variables. Use a one-way ANOVA when you have collected data about one categorical independent variable and one quantitative dependent variable. The independent variable should have at least three levels, such as three different groups or categories. For example, as a crop researcher, you want to test the effect of three different fertilizer mixtures on crop yield. You can use a one-way ANOVA to find out if there is a difference in crop yields between the three groups. A two-way ANOVA is used to estimate how the mean of a quantitative variable changes according to the levels of two categorical variables. Use a two-way ANOVA when you want to know how two independent variables in combination affect a dependent variable. For example, you are researching which type of fertilizer and planting density produces the greatest crop yield in a field experiment. You assign different plots in a field to a combination of fertilizer type, such as fertilizer A, B, or C, and planting density, such as low density or high density, and measure the final crop yield at harvest time. You can use a two-way ANOVA to find out if fertilizer type and planting density have an effect on average crop yield. Multivariate ANOVA or MANOVA extends the capabilities of analysis of variance by assessing multiple dependent variables simultaneously. ANOVA statistically tests the differences between three or more group means, but it can assess only one dependent variable at a time. This limitation can be an enormous problem in certain circumstances because it can prevent you from detecting effects that actually exist. MANOVA provides a solution for this limitation by testing multiple dependent variables at the same time and offers several advantages over ANOVA. Suppose you are studying three different teaching methods for a course. This variable is your independent variable. You also have student satisfaction scores and test scores. These variables are your dependent variables. You can use a MANOVA to determine whether the mean scores for satisfaction and test differ between the three teaching methods. When you perform a series of ANOVA tests because you have multiple dependent variables, the joint probability of rejecting a true null hypothesis increases with each additional test. Instead, if you perform one MANOVA test, the error rate equals the significance level. Correlation tests check whether two variables are related without assuming cause and effect relationships. This can be used to test whether two variables you want to use in, for example, a multiple regression test are autocorrelated. The bivariate Pearson correlation produces a sample correlation coefficient which measures the strength and direction of linear relationships between pairs of continuous variables. By extension, the Pearson correlation evaluates whether there is statistical evidence for a linear relationship among the same pairs of variables in the population, represented by a population correlation coefficient. The Pearson correlation, also known as Pearson product moment correlation, it is a parametric measure. For example, you can use Pearson correlation to measure the strength of the relationship between latitude and temperature. The chi-square test of independence determines whether there is an association between categorical variables, or whether the variables are independent or related. It is a non-parametric test. This test is also known as chi-square test of association. This test utilizes a contingency table to analyze the data. A contingency table, also known as a cross-tabulation, cross-tab, or two-way table, is an arrangement in which data is classified according to two categorical variables. The categories for one variable appear in the rows, and the categories for the other variable appear in columns. Each variable must have two or more categories. Each cell reflects the total count of cases for a specific pair of categories. For example, you can use chi-square test of independence to determine whether there is a correlation between membership in a sports team and membership in a drama club among high school students. Non-parametric tests don't make as many assumptions about the data and are useful when one or more of the common statistical assumptions are violated. However, the inferences they make are not as strong as with parametric tests. Non-parametric tests are also called distribution-free tests because they don't assume that your data follow a specific distribution. The main non-parametric tests are one-sample sign test, Mann-Whitney U-test, Kruskal-Wallis H test, Friedman's test, and Spearman rank order correlation. They are like a parallel universe to parametric tests. The sign test, or one-sample median test, is a statistical test to compare the sizes of two groups. It is an alternative to a one-sample t-test or a paired t-test. The one-sample median test checks whether or not there is a significant difference between the hypothesized median and the real median of a sample. It can also be used for ordered or ranked categorical data. The Mann-Whitney U-test is the non-parametric equivalent of the independent samples t-test. While the t-test makes an assumption about the distribution of a population that the sample came from a normal distributed population, the Mann-Whitney U-test makes no such assumption. The result of performing a Mann-Whitney U-test is a U-statistic. The Kruskal-Wallis H test is the non-parametric alternative to the one-way ANOVA. The H test is used when the assumptions for ANOVA are not met. It is sometimes called the one-way ANOVA on ranks, as the ranks of the data values are used in the test rather than the actual data points. The test determines whether the medians of two or more groups are different. The test statistics used in this test is called the H statistic. The Kruskal-Wallis test will tell you if there is a significant difference between groups. However, it won't tell you which groups are different. For that, you will need to run a post hoc test or a multiple comparisons to uncover the specific differences between the groups. Friedman's test is a non-parametric test for finding differences in treatments across multiple attempts. Basically, It is used in place of the two-way ANOVA test when you don't know the distributions of your data. Friedman's test is an extension of the sign test used when there are multiple treatments. In fact, if there are only two treatments, the two tests are identical. The Spearman rank order correlation is the non-parametric version of the Pearson correlation. While Pearson correlation evaluates the linear relationship between two continuous variables, Spearman correlation evaluates the monotonic relationship between two continuous or ordinal variables. In a monotonic relationship, the variables tend to change together, but not necessarily at a constant rate. The Spearman correlation coefficient is based on the rank values for each variable rather than the raw data. With that, I would like to end this presentation. Thank you so much for joining me in this lecture. Thank you.